Hello again, I'm Engineer Mikko de Torres, and in this video, we're embarking on an exciting journey to uncover the diverse world of mechanical manipulator types. Get ready to discover the incredible variations and functionalities that these manipulators bring to the field of robotics. Let's dive right into the heart of mechanical manipulator types. In this video, we'll explore these manipulators through various lenses, uncovering their unique attributes. We'll dissect the types based on their motion characteristics, power sources, control methods, orientation of joints, and the number of degrees of freedom. As we delve into the world of mechanical manipulator types, let's begin by focusing on the fundamental aspect of motion characteristics. Here we'll explore how different types of manipulators exhibit varying motions, such as linear, rotational, or a combination of both. These distinct movement patterns define the manipulator's capabilities and applications. Imagine a manipulator where all the moving links operate within parallel planes. Such manipulators are aptly named planar manipulators. Their unique design enables motion constrained to specific planes, often found in applications where a two-dimensional movement is essential. Then, imagine a manipulator where one of or more links possess complex and unrestricted spatial motion. These versatile manipulators, known as spatial manipulators, can navigate in three-dimensional space, offering intricate movements essential for various applications. As our journey through mechanical manipulator types continues, let's now delve into the aspect of power sources. Here we'll examine how different types of manipulators are powered, whether through electric motors, hydraulic systems, pneumatic mechanisms, or even a combination of these sources. The power source plays a vital role in determining the manipulator's strength, speed, and efficiency. Imagine robots propelled by DC or AC servo motors, gaining popularity due to their cost effectiveness, cleanliness, and quiet operation. These electrically powered manipulators offer precision and versatility. Hydraulic actuators shine in lifting heavy loads, yet they come with downsides like fluid leakage, additional equipment maintenance, and noise. Lastly, pneumatic robots stand out with their cost efficiency, rapid response, and simplicity. However, they lack precise control and versatility, limiting their application scope. In our quest to understand mechanical manipulator types, let's shift our focus to the intriguing realm of control methods. Here we'll delve into how different types of manipulators are controlled, from manual control to semi-autonomous and fully autonomous systems. These methods define how the manipulators interact with their environments. Imagine the earliest robots operating as non-servo devices. These open-loop mechanisms move within predetermined mechanical limits, primarily suited for basic material handling tasks. Servo robots mark a leap forward with closed-loop computer control enabling multifunctional, reprogrammable capabilities. This category includes point-to-point robots where motion is guided by a controller, facilitating precise and versatile actions. Within the realm of servo robots, let's zoom in on a fascinating category, the point-to-point robots. Imagine a robot that can be trained to navigate between specific points, yet lacks control over the trajectory between those points. These robots are often taught a sequence of points using a teach pendant, a handheld device. The stored points can then be replayed, guiding the robot's movements. Then, Imagine a robot with the ability to precisely control the entire path of its end effector. These robots can be trained to follow straight lines between points or even trace complex contours, such as welding seams. Moreover, the velocity and acceleration of the end effector's movement can often be finely tuned. Let's continue our exploration of mechanical manipulator types. Let's shift our focus on the intriguing aspect of joint orientations. Here we'll delve into how the arrangement of joints impacts the manipulator's motion capabilities, from parallel joints to orthogonal and serial arrangements. These configurations play a pivotal role in determining the manipulator's movement freedom. Let's take a closer look at the category defined by the orientation of joints, serial manipulators. Imagine manipulators where joints are connected in a series, each joint attached to the previous actual joint or the base. In this arrangement, each actual joint is linked to the next actuated joint or ultimately to the end effector. Within the realm of joint orientations, let's dive into the intriguing world of Cartesian manipulators. Picture a robot known as rectangular, rectilinear, or gantry manipulator. It possesses the unique ability to maneuver its end effector within a cube or cuboid workspace. The first three joints are prismatic, allowing movement along the three Cartesian axes. The kinematic description of this manipulator is elegantly simple, making it particularly useful for tasks like material transfer and tabletop assembly. As we continue our journey through joint orientations, next is the cylindrical manipulators. Imagine a robot with the first joint capable of revolute rotation about the base, while the second and third joints provide prismatic movement. This configuration allows the robot to navigate using cylindrical coordinates. With its rigid structure, this manipulator stands out for its capacity to handle substantial payloads and deliver impressive repeatability. Next is the spherical manipulators. Visualize a robot equipped with two rotary joints and one prismatic joint. The spherical manipulator, also known as polar manipulator, features three mutually perpendicular axes, the Z0, Z1, and Z2. This configuration facilitates movement in spherical coordinates. While the spherical manipulator once held its ground, it has relinquished practicality in the workplace, yielding to the versatility of six-axis articulated manipulators. As we uncover more about joint orientations, let's dive into the dynamic world of articulated manipulators. Envision an industrial robot characterized by rotary joints, also known as revolute or anthropomorphic manipulator. Articulated robots span a spectrum from simple two-jointed structures to complex systems with numerous interacting joints. Within the realm of RRR manipulators, we encounter three revolute joints. The axes of the second and third joints are parallel, while the axis of the first R joint is vertical. This arrangement bestows these manipulators with significant movement freedom, all within a compact space. In our final dive into joint orientations, let's delve into the world of SCARA manipulators. SCARA, or Selective Compliant Articulated Robot for Assembly, shines as specialized RRP manipulator. Notably, the axes of this arrangement, Z0, Z1, and Z2, are paralleled. Specially crafted for assembly operations, the SCARA manipulator design allows for precision work and rapid assembly for packaging tasks. Let's now delve into the realm of parallel manipulators. Within this category, Each actuated joint is attached both to the ground and the end effector, creating a distinct mechanical configuration. We encounter two common types of parallel manipulators, the Stewart or Goff platform and the Delta manipulator. These manipulators embody unique designs that offer specialized advantages in various applications. Let's focus on the remarkable Stewart or Go platform, invented by Go in 1947 and later refined by Stewart in 1965. This platform emerged as an ideal choice for flight simulators. To this day, it remains a cornerstone of flight simulations. The platform itself serves as the end effector, creating a unique configuration. The joints primarily feature prismatic linear joints and hook or spherical joints. As we uncover the legacy and applications of the Stewart or Go platform, we gain insights into its significance in the world of robotics. Lastly, let's delve into Delta Robot. Primarily employed for tasks where robots need to pick products in groups and arrange them in containers or specific assembly patterns, the Delta robot is a marvel of efficiency. Characterized by the use of revolute joints, this design ensures precision and rapid movement, making it an asset in high-speed and intricate applications. As we delve into the world of Delta Robot, we unearth its specialized role and contributions to industrial processes. In our exploration of mechanical manipulator types based on motion characteristics, power source, control methods, and joint orientations, we've journeyed through a spectrum of ingenious designs that drive various industries forward. But our journey doesn't end here. Stay tuned as we dive into the final dimension of our exploration, the fascinating realm of degrees of freedom.